there are two types of Marie Curie fellowships, postdoctoral fellowships. One is the European Fellowship, which meant to hire a researcher up to a maximum of 24 months in an European institution. And then there is the global fellowships. The global fellowships, you can have an outgoing phase from a maximum of 24 months in a third country. This is a country that is not a European Union country or a country associated with Horizon Europe. So you have a maximum of 2 years outgoing phase for this third country, and then you have a mandatory 12 months return phase to a member state of the European Union or Horizon Europe associated country. So on top of this, you can have the possibility to have a non-academic placement at the end of the project for a duration of up to 6 months.
But it's very important that you answer all these points, because we as evaluators, so right now we got our first proposals, and we really evaluate exactly on these points. So on quality on of the project. So is it excellent? Is it logical? And this is something that you probably, if you write a proposal, then it's clear that you want to write, oh, it's the greatest proposal ever, it's novel, it's innovative. But then I see very often that people forget these 2 points. So is the host group where you are going, incoming or outcoming or secondment? What's the quality of that research group? And then maybe some people still think of that, but you have to be, and was very nicely explained by David, this two-way transfer. What do you bring to your hosts? What do your hosts give to you? So it has to be interesting to read. We read a lot of proposals, and if it's not interesting, you basically shut down. If English is not your native language, have someone check it. There are so many of your colleagues in the group that check. Don't put 200 references there, because again, that's a space limitation. Make it interesting with bold and italic. And really, really, really don't forget, why do you choose this host? Who is your host? Why are they important? What do you bring to them?
My first tip is apply. Okay, if you don't play, you don't win. It's a very exciting opportunity, and you have seen before that it's not only interesting in terms of science, as well it's very interested in terms of the money that you can earn as postdoc. So I have to say that I start to pay my first house with the money I earn from Marie Curie. So great opportunity in many sense, and stepping stone in your career. Probably today I will not have the position I have as a full professor. If in 2002 I will not get this Marie Curie Fellowship.
You need to learn European Union language, and this is essential. The thing we find most often is that you don't know EU language, and that's then excellent for us, because then we say, okay, this is not correctly addressed. Okay, you need to learn what's the meaning of the wordings, of the words EU is using for the application. This is essential. One of the things we identify at the very beginning of a proposal is when the proposal has been written by the supervisor, or when the proposal has been written by the applicant, by the researcher. All the proposals in MSCA will claim that they have excellent potential application for health, for environmental, for industry, blah, blah, blah. That all of them are green and sustainable, that all of them will create more efficient and sustainable processes, that all of them contain elements of nanotechnology, all the wordings that we use in science. to try to define that we are top. So do not waste your time doing this. Be very specific. You know,
So, few tips from my perspective as previous fellow and as a PI, but since I'm also trying to apply as a PI to supervise Marie Curie Fellowships, why someone should apply for a Marie Curie Fellowship? Because first of all, it's one of the top fellowships you can get in Europe, okay? As previously heard, the money are really good. It's a very prestigious fellowship, but also is your first step. It's a very good first step to become academics, to become independent researchers. In many cases, writing a Marie Curie Fellowship, it will give you the opportunity to reflect what kind of researcher you want to become. It will give you the opportunity to make a plan of your career for the next, I don't know, 5-10 years. Okay, so before you start preparing for a Marie Curie Fellowship, I think it's very important to reflect a bit on that. Not only what kind of specific research project you want to follow, but what kind of researcher, what kind of field you want to be in with the next couple of years. And also, it's the first step of independence. I mean, you might have worked as PhD students in the project of your supervisor. You might have been hired as a postdoc in other projects, but this is one of the first opportunities that you will have to form the research idea and get your own funding and have a project to work on. So very few steps, how I see the application process.
Anyway, from my experience, I consider that there is 3 main key successful factors. First, and this is just my perspective, not the perspective of that I share with other persons, but the main point for me is the idea. The concept of the project should be very clear, very well defined, and ambitious. I think this is the first point that you need to consider when you write a Marie Curie proposal. Second, the Marie Curie application should be planned even during the PhD. We need to have a good background in order to guarantee the success of application. And third, I think is the third point is not less important, but it consists in the consortium. I think the consortium should be well designed in order to effectively match all the purposes of the proposal and help you to reach the main objectives and the main goals.
In general, my PhD has the objective to tailor the properties of bio-based polyesters in order to improve their functional performance for flexible, monolayer, easily recyclable or compostable sustainable food packaging applications. And finally, the gas barrier properties, which are particularly important for food packaging applications, were comparable to the homopolymers of reference, and in some cases even comparable to polyethylene vinyl alcohol, which is the industrial standard for excellent gas barrier properties in food packaging. So in conclusion, the results of this specific work were outstanding. And they represent a step towards the ideal bio-based monomaterial polymeric system, which should be easier to recycle in support to the sustainable model of circular economy, and should decrease the dispersal of plastics into the environment for this reason.
HMF is a versatile molecule with a wide range of application in the pharmaceutical field and in the chemical industries, but unfortunately it occurs in a fast degradation due to the formation of dimers, oligomers, and human during storage. But also the typical degradation condition employed for the HMF synthesis promote numerous secondary reactions such as esterification or esterification. In conclusion, we could achieve a synthesis of bifunctionalized furanics. It was possible to have a reductive amination of both HMF oxime and OBMF oxime to their respective amines. But further studies are currently on to increase the yields and selectivity.
Is to make processes more sustainable. So look in the literature about interesting reaction and processes that are not have a high environmental impact, and look for ways to make these processes more sustainable, either by using biomass or by using more sustainable solvents or less solvents, or less catalysts in different ways, and then further expanding these reactions or processes to new, to a wider scope, to new substrate. Overall, from the preliminary tests we did, we performed approximately like 15 to 20 trials. It seems that we still need a very important excess of acid, but the next step is to check if using a high excess of different acids will give us the product.
Today, in the framework of circular economy, as we all know, worldwide plastic production and consumption, as well as new recycling methods, have gained a critical interest from the scientific community, but the progress that we have made is still little, because several polymers in our days, it doesn't change very well. Anyway, several polymers today are characterized by the release of hazardous substances during their manufacturing process, the use of additives, or during their final disposal, which is associated with a risk to both human and the health of the environment.
So self-healing materials are the ones that are mimicking the nature and are trying to mimic the self-healing process. They are defined as materials that have the ability to repair damage that is created during their life. So the materials that we synthesize have a wide variety of we use different amounts of reactants, different reaction temperatures, different solvents and conditions. And the received materials were characterized by many means, and among them FTIR analysis, DSC, and XRD analysis.
So today, the two major problems that we are facing, which is the depletion of fossil resources and, of course, the plastics and microplastics pollution, are urging us to turn to the use of renewable materials. So to conclude, we successfully synthesized PFA nanocellulose composites in aqueous conditions. We had a significantly increased glass transition temperature and rubbery modulus after the nanocellulose incorporation. We had improved thermal stability of the materials, but we have to further study the materials in order to better understand what kind of interactions we have between sulfuryl alcohol and nanocellulose.
So in the theoretical part, PLA is one of the very most commonly investigated polymers now. It's usually referred as the polymer of the 21st century. It's derived from renewable feedstock such as corn. And its properties involve that it's bio-based, it's biodegradable, and it's, among others, a biocompatible bioester. As we can see from the obtained spectra, we can see that we have the methyl and the methylene groups here at the A2, and in the zoom index, sorry, and in the zoom index here we can see the methyl groups of the lactide. So we can say that we have successfully synthesized the lactide. Now for the 2.5 bis hydroxymethylfuran, we cannot see the peaks very clearly. Maybe we can suspect that we can suggest that these minor peaks here may be attributed to the ester bond from the formation of the copolymer, but we're not quite sure. Further investigation is under progress.
Diminishing petrochemical resources, economic, political, and above all, ecological factors are causing growing interest in the industrial applicability of naturally impure raw materials such as polysaccharides, proteins, and fats. The interest in plant biomass as a raw material is due to its availability, chemical nature, and renewability. Unlike PTF and its copulence PHF and the series of PHF-based copulence exhibited yield point. The PHF and PHF series of copolymers had a high value of encapsulation break than PTF and copolymers based on it. This was due to the higher mobility of the molecular chains caused by a greater number of methylene groups.
The objective of copolymerization is exactly to combine the advantage of each polymer, the high crystallization rate of PPT, and the bio-based nature and the exceptional gas barrier properties of PPF. Because of the presence of the furan ring, this causes a rigidity of the system and enhances rigidity, and we observe that during isothermal crystallization kinetics, the crystallization rate of copolymers was decreased concerning the crystallization rate of PPT. Also, you can see here nice observation of PLM, and it's clearly visible the matrix cross morphology of 95.5 and 92.8 compositions of copolyarses.
Conventional plastics are synthetic polymers of fossil origin and resistant to physical, chemical, and biological degradation. In 2021, in Europe alone, 50.1 million tons of fossil-based plastics were produced, most of which corresponded to polyolefins such as polyethylene and polypropylene. Therefore, it was possible to see some promising differences on the treated polymers, especially on the HDPE without additive treated with buffer, lacase, and DBTS. In the near future, we will try to analyze the liquid phase through high-performance liquid chromatography to understand which monomers might be in the solution, and the recovered samples of HDPE through gel permeation chromatography to evaluate differences regarding the polymer's molecular weight and number.
So as a brief context, we all know there's a global plastic production, enormous global plastic production issue. In 2021 alone, there were 391 million tons that were produced. The vast majority of these plastics are of fossil origin, like it's the case for PET, which is fossil-based and non-biodegradable. In the search for more sustainable alternatives, there's been a rise of the bio-based plastics, and such is the case for PF. However, although they are renewable-based origin, they still have some issues in their end of life. So due to their non-biodegradability and insufficient or inadequate recycling, there's still some persistency of these plastics in their end of life. So as for the main conclusions, we saw that this DS-assisted closed-loop recycling can catalyze both PEF and PET. We reach a maximum yield around 91% for PEF and 98% for PET when we added the DBT, and was also possible to perform the multiple recycling cycles while increasing slightly the intrinsic viscosity.
As you know, the vast majority of plastics used nowadays are essentially fossil-based, and polyethylene terephthalate and high-density polyethylene are in the top 5 most used in Europe. Recycling is one of the best ways to increase the sustainability of the life cycle of plastics, but only 15% of the plastics produced worldwide finished effectively in the recycling centers, being only 35% of those really recycled and less than 1 through chemical recycling. One of the major challenges now in the recycling industries is the recycling of multi-layer packages containing different kinds of plastics, and chemical recycling is in the first line to solve this problem. In this regard, we obtained with this procedure up to 88% of yields of recycling PET, with 100% of recovered of polyethylene, and our recycling PET presented really similar features, not only thermically, but also spectroscopy, in terms of spectroscopy features in comparison with the initial sample and the values already reported in the literature.
For context, we know that our planet is at stake right now, and the polymers are a major contributor to that state of our planet, because their non-biodegradable nature leads to accumulation in landfills and in natural environments. And moreover, they are based on fossil resources most of the time, which is also unsustainable in the long run. So the development of new technologies for polymer recycling is of utmost importance for a sustainable society in the future. And of course, this wouldn't be a Fur for Sustain happy hour if we didn't transpose the know-how acquired from PET to the homologous PEF. And once again, the characterization of our product from this depolymerization of PEF also confirmed that we had our FDCA at the end, so the depolymerization of PEF was also successful. Regarding the yield for TPA was always above 90%, and for FDCA always above 80%, which is overall pretty good results.
As we all know, several FDCA-based polyesters, including PEF and PTF, can be obtained entirely from renewable sources. However, due to their aromatic backbone, these materials should be classified as rather non-biodegradable. So they cannot be decomposed or degraded by living organisms. Instead of that, they perfectly fit in circular economy. They are designed for recycling and further reusing. The research presented here address only the first step of chemical recycling process, which is depolymerization reaction. Optimum reaction time is 3 hours at 180 degrees, with the lowest amount of DES and the highest amount of PDO. What is more, temperature can be considered as the most significant factor affecting the depolymerization reaction of this polymer, whilst the reaction time is the least influential one. In the final step, the proposed optimum conditions were verified experimentally, yielding a conversion exceeding 94%. Knowing that the time does not significantly affect the results, we were curious and we decided to carry out the test again using the lowest value of this parameter, so just 1 hour. And again, we were able to obtain excellent results, and the conversion in this case was around 98%.
Why are we doing this? So first of all, we want to use machine learning. I'm sure everybody of you probably heard of machine learning. It's basically some statistic method, or rather a bunch of statistic methods to be able to predict certain features or variables of data sets. So our current status actually is we're right now at a literature collection, and we have first tests for preliminary algorithms, but so far we lacked a sufficient number of techno-economic assessments because, as you can imagine, the more data we have, the better it will work in the end. So right now we're at the stage. And that's it from my side. Thank you.